Hello, in this video we will cover arc length and curvature. Okay, let's start off with arc length. If you'll recall, in Calculus 2, you went through and derived a formula for finding the arc length of a parametric curve. So since parametric curves and the graphs of vector functions are the same, we want to pick up with that. So the arc length of a parametric curve, x equals f of t, y equals g of t, where t varies from a to b, is given by L equals the integral from a to b of the square root of f prime of t squared plus g prime of t. Squared. Okay, so that's the formula that you went through and derived in Calc 2. So if you're interested in seeing the derivation of that formula again, you need to go and find a Calc 2 video that will cover that topic. So we're just going to assume that that is true. All right, so since a vector function has the same graph as the equivalent parametric equation, we can translate this into vector functions for vector functions. All right, so since the vector function r of t equals f of t I plus g of tj has the same graph as parametric equation x equals f of t, y equals g of t, we can use the result above to find arc lengths for vector functions. So one way that you could do that would be if you started with a vector function, you could convert it into the equivalent parametric equation, and then from there jump and use this formula. However, there's a neat fact, okay, that you can go through and derive, and that is that if we go through and calculate r prime of t, right, so assuming this is r, we're going to get f prime of t I plus g prime of t j. And then if we go through and find the length of r prime of t, a neat thing happens, right? So we take the square root of the sum of the components squared. So square root, we take f prime of t and square it, plus g prime of t and square it. And then take a look at that, take a look at what we ended up with for the length of r prime, and look at our formula, and you can see that those are identical. So we can take the parametric form here and we can actually rewrite it into a vector version all right, where we'd have the integral from a to b of the length of r prime of t dt. Okay, and these are equivalent. Okay, so you can go ahead and use the parametric form by taking the vector function and translating it into parametric, its parametric equivalent, and then using it, or you could just use the vector form without having to do that translation. Okay, let's go through and do a couple examples. So we want to find the arc length of r of t equals 2 cosine t, comma t, comma 2 sine t from 0 less than or equal to t less than or equal to 2 pi. Okay, so if we're going to use this, what we first need to go through and do, if we're going to use the formula, is we need to find r prime, then find the length, and then just pop it into an integral with a and b as the bounds. All right, so first we need to find r prime. And if we do that, so differentiate each one of these. So we're going to get negative 2 sine t, comma 1, comma 2 cosine t. Then we can find the length of r prime of t. That's going to be the square root of the component squared. So we want to take square root and then square each of these. So when we square that first one, we're going to get 4 sine squared. When we square 1, we get 1. When we square 2 cosine t, we get 4 cosine squared. And then since sine squared plus cosine squared equals 1, that means 4 sine squared plus 4 cosine squared is going to equal 4. So we'll end up with the square root of 1 plus 4, which is square root 5. Okay. And now we can go ahead and just take, so that's the length of r prime. It's just the square root of 5. There are no t's in there. That does happen. Okay. And so we just want to go ahead and take that result and pop it into an integral. So we're going to have the integral root 5 dt from 0 to 2 pi, and that's going to be our length. Okay, so if we go through and evaluate that, we get root 5t, 0 to 2 pi, and that's going to be 2 pi root 5. And that's it. Okay, let's try another one that is a slightly harder integral. Okay. Hopefully we have enough room on this page. Oops. Okay, so we want to find the arc length. Here's our vector function, and then here's our range of t values. So just like the last one, we want to find r prime and then the length. So if we differentiate this, we're going to get negative e to the negative ti plus e to the tj plus square root 2k. And then if we find the length of r prime, we're going to get the square root, square each one of these. So when we square this one, we're going to get e to the negative 2t plus e to the 2t plus 2. Okay, and then finally we can take this and pop it into our integral. So we're going to have the integral 0 to 1 equals the square root. Let's try that again. Drawing straight lines can be difficult with the writing tablet. All right, and we get e to the negative 2t plus e to the 2t plus 2 dt. Okay, this can be a tricky integral to do if you've never seen it before. What I can recommend that you do if you have never seen it before, there's a couple of ways you can do it once you have seen it. But if you've never seen it before, what you should do is you should notice this negative exponent. If you take this and take the negative exponent, rewrite it as a fraction, get common denominators, then that might give you some guidance as far as what you should do. And so that's what I'm going to do. Is I'm going to go through and do it that way, rather than to use any of the tricks that that you can use once you've done it a few times. And so yeah, so we're going to go through and we're going to rewrite this, and we're going to rewrite the fraction. So we're going to get 1 over e to the 2t plus e to the 2t plus 2 dt, right? And now once we've done that, we want to get common denominators. Yeah, it's going to be tight fitting this on this page, but let's see if we can do it. If we get common denominators, we're going to get 1 over e to the 2t plus e to the 4t over e to the 2t plus 2 e to the 2t over e to the 2t. Okay, and then let's go over here and combine all that. So we've got, so if we add all these fractions, we're going to end up combining the numerators. I'm just going to go ahead and rewrite them into an order that might be a little more helpful. So we're going to have e to the 4t plus 2 e to the 2t plus 1 over e to the 2t. Okay. And again, if you haven't done this one before, at this point, hopefully that you can recognize that we have something that's quadratic in form, right? So anytime you see something like that, something like this with 3 terms, and the ratio between the first 2 is 2 to 1 like this, where you've got the exponent this exponent is double that exponent, lots of times it's going to end up turning into something that's quadratic in form, and you want to go through and factor it. Okay, so yeah. And so in this case, what this is it's e to the 2t plus 1 squared. And you can go ahead and check that, right? If you multiply that out, you're going to square this, and e to the 2t times e to the 2t is e to the 4t. And then you can use the formula 2 times this, that is the middle term, and then this squared is 1. And so you can see that this squared does work out to that. As far as getting from here to here, the way that you can do that is you can do a substitution. You could go through and say, let z equal e to the 2t, and then this is z squared plus 2z plus 1, and that could get you to the point where you could factor it just using your general factoring knowledge, from polynomials. Okay, so once you get to this point here, we can go through and we can take the square root of both of these, and we'll get the integral from 0 to 1. Then we're going to get e to the 2t plus 1 on top, and we're going to have e to the t on the bottom. And we forgot our dt's here. And then you can go ahead and simplify that. E to the 2t divided by e to the t is going to be e to the t, and 1 over e to the t is going to be plus e to the negative t. And now that you've gotten to this point, now that you've seen the example before, you actually can recognize that if you took this and you squared it, you will get this. So you could, in the future, you could jump right from here to here, because underneath this square root is this thing squared. Yeah, so it's kind of a trick. But if you've never seen it before, then you really kind of have to go on this journey, of going through and getting rid of the negative exponent and simplifying. Okay, so from here we just go ahead and plug in. So we're going to have e to the 1 plus e to the negative 1, and then minus, and you plug in 0, and you're going to get 1 plus 1, right? And so we're going to have e plus 1 over e minus 2. that's a much harder example problem. And so there's two examples of arc length problems for you. Okay, so the next topic we're going to look at is something called arc length parameterization. So in short, what that means is it's going through and parameterizing a vector function using arc length. Now that might be a lot if you're not up on the lingo, you've forgotten some of your parametric equation language. And so let's just kind of go over the basics to try and build up to that, right? So what is a parameter? Okay, so in terms of this review, I'm going to go over parametric equations for the most part, because parametric equations are where we introduce the idea of parameters and parameterizing and doing all these other things. And then at the end, we'll just go through and say anything we can do with a parametric equation, we can do to a vector function since their graphs are the same. And so, right, so what is a parameter? In a parametric equation, x equals f of t, y equals g of t. The parameter is t. So the parameter is the thing that we plug into the parametric equation. So it's the third variable, right? We've got x and y, and they're both defined in terms of t, and the t, that thing that they're both defined in terms of, that is the parameter. So you can go through and reparameterize vector functions by doing a substitution for t. Okay, so how do you go through and do that? Well, the substitution, it's very simple. You could just go through and just take t and you set it equal to something else. So for example, we could say t equals 2w for the parametric equation x equals t, y equals 2t squared. All right, so if we have this parametric equation and then we want to go through and reparameterize it, we could set t equal to 2w. And watch what happens, right? So here's our original parametric equation. And we have x equals t, y equals 2t squared. And then here's our new post substitution. We get x equals 2w, and then y equals 2 times 2w squared. And so this simplifies into 8w squared. Okay, so the thing about going through and doing a reparameterization like this is that as long as the substitution that you make, as long as if you think of the substitution as a function, as long as that function is invertible, then it turns out that the graphs will remain the same. The graph doesn't change, okay, except for one fact, which we'll talk about in a second. All right, so let's just kind of note that, right? So when reparameterizing, with t equals f of w, where f is invertible. the graph does not change. Why invertible? Well, the key thing here is that the new parameterization, right, that you're going through and doing, the substitution that you're doing, it can't have squares in it. It has to pass the vertical line test and the horizontal line test. Otherwise it creates issues, in terms of going through and having X values that if you substitute with a square, you'll have X values that can't be negative that originally could be. And so, you run into all these issues if you have even functions. And so you've got to go through and call all those out. And the invertibility requirement goes through and it does that. It ensures that you can't have two outputs for any input or two inputs for any output. And those are the two situations that would potentially create problems if you were to go through and try and reparameterize. Those are the two situations that would cause a problem with the graph. Okay, and so let's go through and graph each one of these and just go through and prove to ourselves that we do get the same graph. And then I can maybe comment one more time on this to just kind of show what would happen if we went through and tried to use an even function in the substitution. Okay, so we have x equals t, and we have y equals 2t squared. If we were to go through and graph this, the way that you graph it is you eliminate the parameter by taking this and substituting it in place of the t. So we're just going to substitute x equals t for t, and we'll end up with y equals 2x squared, right? And we can go through and sketch that. Right, so that's just a parabola. And it's not quite to scale, but you get the idea. Oh, those are supposed to be a 2, not 1. Okay, and now what if we went through and tried to do the same thing? Right? If we have x equals 2w, and then we have y equals 8w squared, well, we could rewrite 8w squared as 2 times 2w squared. And so this would also, hold on, this would also allow us to go through and just take this and substitute it in there, and then we would get y equals 2x squared. And if you go through and you graph that, is it exactly the same? Let's just think about it for a moment before we just move on immediately. Oops. Well, so here are our two graphs. They look exactly the same. However, one thing to keep in mind, right? So we went through and eliminated the parameter, but that parameter is still in there. And if we were to go through and plug in values, we could go through and figure out what points, correspond to those inputs, right? So for example, if you plug in t equals -2, this is t equals -2 right here. Okay, you can see if you take it, you'll get x equals -2 and y equals 2 times -2 squared, which is 8. If you go ahead and plug in t equals -1, you get this point here. If you plug in t equals 0, there you go, and t equals 1 and t equals 2. Okay, so the parameter is still there. So just because you didn't go through, because you went through and eliminated it, does not mean that there is not that the parameter does not still exist and does not affect the graph, right? So you get a directionality to parametric equations, which is different than just going through and graphing y equals 2x squared by plotting points. And this, and what about this case, right? So if we start off and we go ahead and plug in points, what point corresponds to this value here? Well, it's not going to be -2. It's going to be w equals -1. And here's w equals -1/2, and w equals 0, and w equals +1/2, and then w equals +1. And so there is a difference right here. If you think of t and w, right, if you're going through and you're plugging in values, so to get from one end of this graph to the other, we had to go from -2 to 2. To get from one end of this graph to the other, we had to go from -1 to 1. So if you think about it, this one is being traced out faster, right, per change in w, relative to this one per change in t, right? So you could think about it that way, that this curve is actually being drawn faster than this one. And so the parameterization does produce the same graph, but the graph is drawn over a different time scale, right? If you think about it that way, you know, where this, in this case, as t increments, it goes from here to here. That's one increment. Here to here, that's one. That's one. That's one. And then w, this is one increment, and then this is one increment. And so a single unit goes much further on this graph than on this graph. Okay, so let's just briefly, this is really a parametric equation thing, but what happens if you go through and you wanted to do t equals, let's see here, we'll use t equals m squared. What happens? All right, so in that case, if you go through and this is our original, so we're just popping that in. So we're going to get x equals m squared, and then we'll get y equals 2 times m squared, right? So in that case, we're going to get 2m to the 4th. All right, so this is our parametric equation. So if you go and you look at this, okay, it might seem on the surface like it's very similar to these two. They will work the same way, right? You could go through and here's x, here's y. So we just take x and just pop it right in there, and we'll get y equals 2x squared. And so on the surface, you'd say, okay, well, this is the graph of this and this and this are all the same. Once we eliminated the parameter, we ended up with the same result. However, take a look at x here. X is equal to m squared. M squared. All right. So the problem is if you go through and you plug in negative values for m, you're going to have to square them before you get x. And so what that means is that there's no negative values for x. So if you were to go through and graph this, it does not look the same as these previous two pictures. Instead, what you get is you get just one curve. So you go 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. And so you just get one. You say, how could that work? How could you just get one curve? That doesn't make any sense. And you go through and you graph it, right? So you just get one curve. So how could you have one curve? Where are the negative values? Well, if you start off and you plug in, you know, -1, right? So, or negative, what we got to get here. So if you plug in -1, you're going to be right here. But so maybe that's not a good idea to go through and plug in -1. But if we start off with negative square root of 2, you'll be right here. So this is m equals -√2. And then here we'll have m equals -1. And then here we have m equals 0. And you say, well, what's going to happen here? It doesn't have to keep going. No, it turns around, and then you also get m equals 1, and you get m equals +√2. And so the way that the curve goes, it comes down, hits the origin, and then turns around and goes back. Okay, and again, that's because you used an even function. So in order to have the parameterization not change the graph, like what happened here, then the graph has to pass both, you know, vertical and horizontal line tests. It has to be, you know, what's said to be 1-to-1 and onto, you know, to use some more advanced math vernacular. Okay. Anyway, so that's a lengthy review of parameters and how they work. So what about an arc length parameterization? An arc length parameterization uses a parameter s. So s is the typical letter. Such that if you plug in x of S1, you plug in S1 into your parameterization, and you plug in S2, sorry, into your parametric equation. You plug in S2 into your parametric equation, right? If you go through and do that, then the 2 points on the curve are S2 minus S1 units of distance apart. I'll draw a picture in a second so that might make more sense. Okay, so yeah, let me draw you a picture. All right, so if you have, so you've got a curve, and so we've got this point here is x of S1 comma y of S1. So that's the point that you generate if you plug S1 into the curve. And this point here is x of S2 comma y of S2. That's the point that you generate when you plug S2 into the parametric equation, into the curve. And then so what it means to be an arc length parameterization is it means that the distance between those 2 points is going to be the difference between is going to be the length along the curve that's the difference between the 2 inputs. So if you went through and just shaded this, here's the length between those 2 points. So that length is S2 minus S1. And so that's how an arc length parameterization works. So if you go through and you plug in values to generate the curve, the length between the points that you generate is the same as the difference between the inputs. Okay, so that's what it means to have an arc length parameterization. Now that is not normally true. Okay, if you go back to the previous page, right? If you go through and take this point here and this point here, see how we plug in t equals 1 here and we plug in t equals 2 here. This distance here is not 1 unit, right? So a normal parameterization does not have anything to do with arc length. Okay, it doesn't have anything to do with the length along the curve. The same thing goes for here, right? So if you go through and you take, you know, here's 0, here's 1. So you have this amount of arc length that you traveled to get from w equals 0 to w equals 1, right? That's not going to be 1 unit of length. Okay, so this is a special thing that has to do with, you know, has to do with a parameterization that is in terms of arc length. So in that case, if you go through and you plug in values, you generate points that are the difference in the parameter apart. Okay, now so that's going to turn out to be useful in just a few minutes when we go through and define curvature. So we need that definition for curvature. So all of that was just to build up to define so that we could go through and define curvature. Okay, so one other thing that is in this section is that you can go through and create an arc length parameterization for a vector function. So the idea is that you could be given a vector function, and then there are steps that you could go through to take that vector function and parameterize it using arc length. Okay, so I'm not going to cover that in this video. this video is already going to be long enough, as you'll see. So that's a topic that you're going to have to find another video to cover. Okay, anyway, so the last thing that we're going to do is something that I just said. So since graphs of parametric equations and vector functions are the same, everything I just said also applies to vector functions. All right, so with all that said, all that background created, we now have the information necessary to go through and define curvature. All right, so what is curvature? Let's start off with a definition, right? So the curvature of vector function R of t is a measure of how curvy R of t is. Okay, so that's kind of, self-evident in the name that curvature measures curviness, but it's just important to define things properly. All right. The way that we are going to go through and define it, all right, and we're going to go through the definition carefully to explain how it measures curvature, but it is defined as the amount of change in the unit tangent vector divided by the amount of change in distance along the curve. So if we were to write this out, so the curvature symbol is a K. All right, so what it equals is it equals the change in the unit tangent divided by a change in distance along the curve. And then we're going to go through, and since this is a vector, we're going to find the length of that vector, and that is going to represent curvature. So at a glance, I don't know if it's obvious that this would measure curvature. So it's the amount of change in the unit tangent, right? So we've got the amount of change in the unit tangent per the change in distance along the curve. All right, so change in the unit tangent over change in distance. Okay, so the way that you could translate this, the change in the unit tangent, so you could think of the unit tangent as representing the direction that you're moving in along the curve, right? So it's not just the tangent vector, it's the unit tangent. And so the length has been culled from it. It's length 1. So it purely represents the direction that you're moving in. And so you could think of it as change in direction over change in distance. And if you think about what it means to measure curviness, like how curvy something is, if you think about that, it means to how is the rate that you're changing direction for a change in distance, if you think about it, okay? And so you can go through and prove this to yourself, or I'll prove it to you actually, not just prove it to yourself, but I'll prove it to you by going through and, we're going to jump, we'll do a bunch of stuff to go through and prove it. However, I do just want to be clear that if you actually think about it, if you just draw a curve, right, and think about, all right, well, what does it mean to be curvy, right? Or at least to compare curviness, to compare that curve with, say, this curve. What's the difference between those? Well, this one, my direction has changed. My direction has changed more, right? Like I started off going this way, and I ended up going back the way that I came, right? So I started off traveling this way and ended up traveling this way. So my change in the direction that I was heading in was much greater over the same distance in this thing. And we would say this is much curvier than this, right? So this one, you start off heading this way and you end up heading this way. So if you take the change in the direction that you're moving in and you divide it by how much distance you travel to make that change, that really is how we would measure curviness. However, let's go through and kind of prove this in a little bit more in a little more depth. Okay. Partly because I want to show you a method that you can use. Okay, so this is a neat method, right? So we know that curvature equals dt ds. All right, so what I want to do is I want to strip out that dt ds, and let's just ignore the length bars here for the moment. All right, so we've got dt ds. So a trick that you can use to go through and study things in calculus that that maybe are confusing or not clear on the surface is you can go back to the definition of the derivative, right? So this equals the limit as change in s goes to 0 of change in t over change in s. So if you've never seen the derivative written this way, this is the rate of change form, right? So this is a rate of change, and this is the rate of change form for the derivative. Now it's a little bit different than the h form, right? Where you've got f of t plus h minus f of t over h. So that's the regular function form. That's like the slope form. Well, actually, they're both slope forms, but this is what we think of as a rate of change, a change in t over a change in s. And so when you take the limit as change in s goes to 0, this becomes an instantaneous rate of change. So we call this the result of the limit. We call this the instantaneous rate of change. This is all Calc 1 stuff. And meanwhile, this without the limit, we would say is the average rate of change. So again, without the limit, right? So average rate of change. That's all very, very beginning of Calc 1 stuff. And so you can go and convert from an average rate of change to an instantaneous rate of change by throwing this limit in here. But what does this mean? This means that this thing, our instantaneous rate of change, if we ditch the limit, these would be approximately equal, right? So, oops, not D there. And so it allows us to go through and change this, the derivative here into something that has this alternate format. And this alternate format here is much easier to wrap your head around and understand what's going on, in the calculations, the underlying calculations. Why is that? Because we can go through and rewrite change in s over change in t as s or t of s2 minus t of s1 divided by s2 minus s1. And so we started off with a derivative and we ended up with something that looks kind of like a slope, or it's a change in quantity divided by a change in another quantity, a rate of change. And so that will enable us to kind of go through and study the underlying thing in better depth. All right, so let's do that now, right? So we went through and we have the curvature is the length of this, and we said that this is approximately equal to this, and we said this equals this. So that means I can look at this calculation and say something about what the curvature would be. Okay, and so let's see if this calculation does go through and measure curvature. Let's see if these two things align and they do the same thing. Okay, so the way that we can do this is we could start off with, let's say we have a straight line. Let's say that we have a curve with some bend to it, and these are supposed to be the same length. And then let's say that we have a curve with a lot more bend to it. Okay, so in this case, right, we want to go through and put some points on here. We're going to say this point is S1 and this point is S2. And not only that, but our curve is parameterized by arc length, which means that this distance between the 2 points is S2 minus S1 units of distance, right? So this is S2 minus S1 here. Okay, and now what I'm going to do is I'm going to go through and I'm going to say, all right, well, what is the unit tangent here? Well, the unit tangent on a straight line, right? So we're going to say the unit tangent here, it's going to look like, this, right? Okay, and then we could say the unit tangent here, again, straight line, it's going to look like that. Okay, and so if we're going through and measuring how curvy this line is, and what we've been saying is that the measure of curviness is how much change there is in the direction that we're facing, how much change there is, in these unit tangents. Well, how much change is there? All right, so if you go through and take these two vectors and you subtract them, what happens if you take t of S2 minus t of S1 and you subtract them? Okay, well, they're the same vector with a line, and so we end up with the difference between these two. If you just go through and subtract them, right, knowing what we do about vectors, if you take this vector here and you subtract the same vector, then you end up with 0. And so we'll get 0 over S2 minus S1. And so our calculation for how curvy this was, which is, was by this formula here, ended up being 0. So how curvy is a straight line? Well, it is 0 units of curviness, I would think. So our result kind of made sense. So this formula here did go through and calculate how curvy it was. Calculate the curviness. The curviness of a line is 0, and we got 0, so that's a good check mark there. And now let's go through and do the same idea on this picture, right? So again, we're going to go through and we have S of 1 and we have S of 2. And again, this is parameterized by arc length. So this distance here is S2 minus S1. And then at this point here, we have T of S1. And here we have T of S2. That's the unit tangent at that point. What do those unit tangents look like? Well, this one looks like this, right? About like that. And then if we were to go through and draw one here, it looks about like this. Okay. And so if we were to go through and calculate this quantity, right? So T of S2 minus T of S1 over S2 minus S1. Okay, well, what do we get if we subtract these? Well, let's go through and do that, right? So we know how to subtract two vectors. You put the starting points as the same. So here's T of S1. Here's T of S2. About like that. Okay, and then the difference between them is going to be, right? So it's going to be this vector here. All right, so what is this vector? This vector is the change in direction, the amount of change in direction there was, right? If you think about what's going on here, you start off going in this direction, and then here at S2, you're going in this direction. So how much change in direction was there? You're driving your car, you turn the wheel, all right? So you started off going this way, you ended up going this way. So in terms of your path that you took, the change in your direction would be the difference between the direction that you were moving your car in at the first spot, right? So we're not thinking of time, but the first location and then at the second location. So this is the change in direction. Now, if you go through and think about this, so that's in the numerator. So what do we have here? TS2 minus TS1, that's this, right? So if you look at that, it's a relatively small amount, right? So you'd say it's a small vector over S2 minus S1, okay? And if you look at this curve, right, how curvy is this curve? Not very. So if we get a small change in direction, then that corresponds to a small vector, right, in terms of the numerator, how much directional change there is, over the distance that you traveled, the length that you traveled, right? So how far did you travel from S1 to S2? It's S2 minus S1 units. Again, that's that arc length parameterization. So here we traveled S2 minus S1 units. Here we traveled S2 minus S1 units, and then we're going to do S2 minus S1 units here. So to be consistent on all of them, that arc length parameterization allows that consistency. Okay, and so let's go ahead and see what happens on our third picture here. So if we go through and pick some point, we'll say this is S1, and then we want to pick about the same distance. So it looks like, I don't know, maybe here. And we'll say that's S2, okay? And now what direction are you heading in here at S1? Well, you're heading this way, okay? And that would be T of S1. And then what direction are you heading in here at T of S2, right? You're heading this way, right? So that would be T of S2. Oh, actually, hold on. Let me move the S2 to the other side. So here's S2. Here's T of S2. And then if you go through and think about, what we would get in the numerator for this case, so T of S2 minus T of S1. So that's, again, going to be the difference of those two vectors. How do you calculate the difference of vector? You have them start off at the same initial point. All right, so there's T of S1. And then here is T of S2. And how much change in direction was there? So you're going this way initially, you're going this way, and now you're going this way. So how much directional change has there been between the two? Okay, well, the directional change is going to be this vector here. Okay, and so what we end up with, if you go through and in the case where you have a larger curve, you're going to end up with a large vector over this, again, the same distance, the consistent same distance in the denominator of each one of these. And so we have a large amount of change in the curvy case where the vector curves a lot. Your directional change, the direction that you're moving in, is going to change a lot as you go around the outside of the vector. And so if you go through and calculate the difference in those vectors, you end up with a large vector in the numerator. And so thus, if you go through, and now don't forget these lengths here, if you go through and throw the lengths around this, this produces a small quantity. And if we throw lengths around this, this produces a large quantity. And of course, if you throw lengths around this, you still get 0. And so you can see that this notion, right, of having the change in direction, which is the same thing as the change in the unit tangent in the numerator, over a change in distance, a change in length along the curve, like how far you move along the curve. Change in direction over change in distance is curviness. That is curvature. That is how we would measure how much we curve as we move along, a curve. And so anyway, so that's all of this explanation is just to go through and show you that, yes, this is the right metric for going through and defining curvature. This does work. It does do the job and produce a measure of curviness, right, which is what we said our goal was. So the curvature of a function is the measure of how curvy. All right, well, how curvy is it? That's determined by that quantity. Okay. Now, so one of the things that you'll notice is that throughout that example, I kept referring to the arc length parameterization and using the S and the distance along the curve. All right, well, what happens if we do not have a parameterization by arc length? All right, so how do we use curvature? When there is no arc length parameterization? Okay, well, what we can do is we can convert the arc length parameterization into a parameterization, a neutral parameterization. Okay, and how do you do that? Well, you use one of the cool facts of calculus, right? The fact that calculus works like algebra. Oh, and the reason calculus does work like algebra is this, all of this stuff that's here. So if you've never wondered why does calculus work like algebra, it's because a derivative harkens back to something that is an algebraic quantity. We have a change in t over a change in s. Okay, and then so anything that you can go through and algebraically do to this, you can also do with a derivative. That's exactly why. It's nice to have them both kind of that to be in the lecture. So anyway, so what it allows us to do here is we can go through and say we could take dt ds. Okay. Oh, whoops. Hold on. We can take dt, right, like that, and we can multiply it by dt ds, and these two are equal. And so you could see here, I could cancel these middle two and I could get back to this. All right, and so you can go through and you can do this kind of thing with calculus where you can just go through and do an algebraic manipulation like that. And again, the reason why, this is the reason why. Okay, it's because you could take dt over dt and you could make it change in t over change in little t, and then this is change in little t over change in s, and then the two do cancel. The little change in t's cancel. Okay, and so anyway, once you've gone through and done that, we can rewrite this into the following format. This is dt divided by ds dt. Okay, and so I just have manipulated it to put it into this form, turn it from multiplication into division. All right, and now at this point, you can actually split this. So this is the going through and finding the length of the resulting vector here. What we have is we have scalar multiplication, because this is a scalar. You can peel off that scalar out of the scalar multiplication. It's scalar division, but multiplication and division are, you can represent multiplication with, you can represent division as multiplication by the reciprocal. And so this is the same thing as scalar multiplication. You can pull that out with an absolute value and split this so that you've got, now you're finding the length of the vector, right, in the numerator. And then you're finding now it's the absolute value of the quantity in the denominator. Okay, and again, so why would that happen? Well, if if you want to think about what this length quantity is doing, it's taking the square root of the components squared. Okay, if you pull this out of the square root of the component squared, right, it's going to come out as an absolute value because the result of a square root is going to be positive. So I hope that makes sense, right? If you pull this out of the square root that is defined by these two, then the result is going to be a positive quantity. So that's why we have a positive quantity down here. Okay, and now where this gets a touch tricky is we can go through, and this is the derivative of t with respect to t. We can go through and we're going to replace that with t prime of t. And then in the bottom, this is going to seem like magic, but we're going to go through and we're going to define that as r prime of t. Okay, and if you're wondering where that comes from, where does that r prime have come from? How did we go from ds dt to r prime? Okay, well, if you go back to our arc length definition, right? So we have the integral r prime, and I'm going to use u instead of t. If we define that as a function, right, from a to t, and we say that we have s of t is that function. Okay, so if you go through and define arc length as a function like this, where you could plug in t values and out would come arc length, right? So if you plug in t equals 5, you get the arc length from a to 5, and that's going to be a number. If you plug t equals 10 in, you get the arc length from a to 10, and that's going to be a number. And so what we've got is a function here where for each t input, out comes an arc length. If you go through and differentiate this with respect to t on both sides, the derivative of s of t with respect to t and the derivative of the integral from a to t of the length of r prime of u du. Well, on this side, the derivative with respect to t of function s is just ds dt. And then on this side, if you have the derivative and an integral back to back, by the fundamental theorem of calculus, these two cancel and we end up with r prime. And now you do have to change the variable here because the t here is in the bounds. This is a function. And so you plug in the t in when you go through and do that. And so we end up with the SDT equals the length, and then that's where it comes from. So it comes from going through and starting with a arc length function and then differentiating both sides of it. So it is kind of a little bit like magic, going through and doing the manipulation here. But you've got that neat algebraic formula from calculus that allows you to introduce these dt's. Then you separate them, and then you can substitute. And so all of this is to get to this result. So all of that explanation for the past however many minutes was to get to this formula, explain where this formula comes from, why it works, and so that's our curvature formula. All right, so let's go through and do an example to try and calculate curvature. All right, so we have, let's start off. So we have r of t equals, we're going to use the same example from earlier. 2 cosine t, t to sine t. Okay. And so we want to go through and, actually, let's just transcribe it. We want to calculate this. So we want t prime of t over r prime of t, like that. Okay, so to do that, first of all, we start with r. We need r prime at some point because we want to find that in the bottom. Wait, hold on. These lines need to be on top and bottom. All right, so we need r prime. So we get -2 sine t, 1, 2 cosine t. All right, and so that gets us this, and then we go through and find the length, and then we'll be done with the denominator. So So what is the length of this? We're going to get the square root of 4 sine squared t plus 1 plus 4 cosine squared t. I guess we could have copied earlier what we did. And then this will be square root of 5, right? That's the same result we got earlier from the earlier example. Now, to go through and find the length of the unit tangent, we first need to build the unit tangent, right? So if you recall from the previous video, we have the unit tangent is r prime divided by the length of r prime. Okay, so we can go through and use these previous two results to define the unit tangent. It's going to be negative 2 sine t, comma 1, comma 2 cosine t, all over the square root of 5. So this is negative 2 over root 5 sine t, 1 over root 5, and then 2 over root 5 cosine t. And then once we have the unit tangent definition, we need to go through and differentiate it. And so if we do that, we're going to have negative 2 over root 5 cosine t. The derivative of 1 over root 5 will be 0. And the derivative of 2 over root 5 is going to be negative 2 over root 5 sine t. And then finally, we need the length of t prime. That will be the square root of the components squared. Right? So we're going to have 4/5 cosine squared t plus 4/5 sine squared t. And that equals the square root of 4/5, which is going to be 2 over root 5. And then once you've done all of that, you can go through and calculate the curvature. And it's going to be the length of t prime over the length of r prime. So the length of t prime is 2 over root 5. And the length of r prime is root 5. And you flip and multiply, and you get 2/5. So a bit anticlimactic there at the end. All the heavy lifting was done in these previous steps, but that's the curvature. So in this case, how do you interpret that curvature? Right? So if you haven't done many curvature examples, in this case, we ended up with a constant curvature. Right? So constant curvature occur in things that act like circles. It's really no surprise if you look back at the original that this thing does act like a circle. Right? So we defined this in a previous section. This is the helix. All right, and helixes do behave like circles, and they do have constant curvatures. So do you always end up with a constant curvature when you're going through and using this? No. If you're working with something that doesn't have a circle basis to it, then here at the end you'll have t's in your curvature result. And then in that case, you could think of the curvature as a function where you could go through and plug in a t input and then get out a curvature for that t value. Okay, and so if you have it, if for example we'd had this was 2/5 plus t, just hypothetically, then this would be, you could think of this as a function, all right, and then you could plug in 1, and then you'd get the curvature at t equals 1 is 7/5. And so that's how it would work if you did end up with a t value in your curvature. Okay, and now so. Is that it for curvature? No, it's not. So it turns out this calculation, you may have noticed, there's a lot here. This can actually get very, very messy if you have functions that are not don't have circles as a basis for them. If we'd gone through and applied this to any old function, these calculations can become quite horrible. And so because of that, there is an alternate formula. So I'm not going to go through and generate the alternate formula. I'm not going to go through and prove it to you that it's equivalent to the previous formula. You can go through and you can look that up. As I said, this video is already going to be long enough, but the alternate formula is given by the length of r prime of t cross r double prime of t divided by the length of r prime of t cubed. And so this formula has some nice nice things about it. For one thing, it's all derivatives of r. We don't need to go through and find the unit tangent, and that is going to make the calculations significantly simpler because of that. And so let's go through. We can do the same example. This example might not be much different because of the fact that it has, because it's got a circle basis. But if you're going through and you're working with something that's not a circle, then this new alternate formula can be a lot better. All right, so what do we need? We need r prime, right? We've already calculated r prime. It's on the previous page. What is r prime? It's -2 sine t, 1, 2 cosine t. So we get -2, wait, was it -2 sine? Yes, -2 sine t, comma 1, comma 2 cosine t. And then now we need r double prime. So that's going to be -2 cosine t. Derivative 1 is 0. And then -2 sine t. And then we can go through and calculate r prime cross r double prime. That is going to be equal to the result of the determinant, right, of the 2 by 2 matrix, or 3 by 3 matrix. We've got I, J, K, and -2 sine t, 1, 2 cosine t, and -2 cosine t, 0, -2 sine t. And if we do that, we'll have I times -2 sine t minus 0 minus j, and that's going to be +4 sine squared. And then minus a double negative, so we're going to have +4 cosine squared. And then plus k times 0 minus -2 cosine t. So we're going to have +2 cosine t. Okay. And then we need the length of r prime cross r double prime. So that's going to be the length of that vector. And what are we going to get for that? So we'll have the square root of the component squared. So this first one, we're going to get 4 sine squared. This 4 sine squared plus 4 cosine squared, that's just 4. So we're going to end up with plus 16 when we square it. And then we'll have 4 cosine squared. And if we combine the 4 sine squared and 4 cosine, we just said that's 4. So that's 4 again here. And so we're going to end up with the square root of 20. Okay. And on the previous page, we already have gone through and found the length of r prime. What was the length of r prime? Length of r prime was square root 5. Let's just transcribe that over rather than do that again. Root 5. And then so our curvature is going to equal root 20 over root 5, right, to the third power. Don't forget that third power there. So we're going to get root 20 over 5 root 5. And then you can break this up into, this is 2 root 5 over 5 root 5. And you get 2/5. So that might not have been much less work. That maybe seemed like a little bit less, but it might not have been much less work than this previous one. But again, if you'd had something that was not a circle, then it becomes nightmarish to go through and find the unit tangent and differentiate it and divide by the length. If you've got t's left in here and they're not inside sines and cosines, then it's quite ugly. Meanwhile, you don't have to go through and find the unit tangent or differentiate it over on this side. And so this calculation is just much simpler. Okay, there's one more topic that we're just going to squeeze in here at the end of this video, and that is the unit normal. What is the unit normal? It is a unit vector that is orthogonal to the unit tangent. Okay, and also, I'll mention, I'm going to add on to this in just a second, but it's not going to make any sense until you actually see a curve. All right, so let's go through and draw a graph, and you can see visually what does the unit normal look like, right? So let's say we've got our curve here, and it looks something like this. Okay, so here, right? So we could go through and we could say this is the unit tangent. Okay, and we could say, here we've got the unit tangent, and here, we've got the unit tangent. And so on, right? So we've got a bunch of unit tangents on here. So those are all familiar. We're familiar with all of those. So here's, t at that point, t at that point, t at that point, t at that point. All right. What does the unit normal look like? So the unit normal is orthogonal to the unit tangent. All right. So orthogonal. We want to draw something that's at a 90-degree angle to this. Okay. And what do we end up drawing? We end up drawing this vector, right? So you can see that we do have a 90-degree angle there, right? So that's the unit normal. It is orthogonal, right? So here, the vector that we would get is that, we would get that vector. So that is the unit normal. And here and here. Okay. Yep. All right, so that is the unit normal. So if the unit tangent points the direction that the curve is heading, then the unit normal points into the curve. All right, and that's the piece that I'm going to add here. It points into the curve. Right, so what I mean by into the curve. So the curve is this way, right, and it's pointing inward. So outward, if the curve is oriented this way, then outward would be this direction. So it's pointing into the curve. Okay, so what is the formula? So all of this is what the unit normal is. How do we calculate it? The unit normal is defined by it is the derivative of the unit tangent divided by the length of the unit tangent. Right, so that is the formula. And if you look at that and you say, that formula produces the vector that is orthogonal to the unit tangent? Yes, it does. So we do want to go through and prove that, all right, that this formula, which is it's kind of fascinating, right? So to produce the unit tangent, you take the derivative of the original function and divide by its length. And then to produce the unit normal, you take the derivative of that result and divide by the length. It's kind of shocking that it does work that way, but it does. All right, so let's go through, and on the next page, let's prove that unit tangent and unit normal are orthogonal. This is a nice, I like this proof. It's quite simple. It does require a little bit of background information from earlier in the semester that we didn't really get into. So there are some properties of the dot product that we did not go through and prove absolutely every single property. So here is an example of one of those properties. So let's say if we had A and it's A1 comma A2. All right, then what the property says, if you go through and do A dot A, that is going to equal, right? If you dot product A with itself, then you're going to get A1 squared plus A2 squared, right? And then if you go through and simplify that, we'll simplify it. What you can do with that is you can go through and do the following. We can take the square root of A1 squared plus A2 squared and square it, and you'd get the same thing as that, right? So you could take this and convert it by square rooting and squaring. All right, and then if you do that, then what is this? This is the length of A, And so we end up with the length of A squared. And that is one of the dot product properties. So we didn't go through and prove that one, but A dot A equals the length of A squared. Okay, and let's look, and there's another one. All right, so there's a bunch of little properties here and there that we did not go through and prove. But if we have, let's say we have R1, and that's equal to F1 of t, comma, G1 of t. So we have a vector function, and we have R2, and that's equal to F2 of t, comma, G2 of t. All right, if I went through and did R1 and dotted it with R2, what happens? So you end up multiplying these and adding the results. So this is, I'm just going to use a little shorthand here. So it's okay, we're going to get F1, F2 plus G1, G2. All right, now if you went through and differentiated R1 dot R2, what would happen, right? So if we went through and took the derivative, right, these are just regular old scalar functions. And so we can go through and take the derivative of those using our Calc 1 techniques, right? This is just a function of t times another function of t, and we're differentiating with respect to t, right? So to go through and do that, we want to use the product rule. So we get the first times the derivative of the second plus the second times the derivative of the first. And then do the same thing for g. We're going to get the first times the derivative of the second plus the second times the derivative, that should be a g, times the derivative of the first. Okay, and now if you look at this, right, so what is this first, these, ignore these second two, but what is this first group, right? What is that this group is we've taken F1 and G1 and we've multiplied it by F2 prime and G2 prime. And so that is the dot product of R1 and R2 prime, these two. And now here we've got F2 and G2 and F1 prime and G1 prime. Here we've taken the vector F2 G2 and multiplied it by the vector G1 prime, F1 prime, G1 prime. And so that is the result of the dot product of R1 prime and R2. And so long story short, the way that you can go through and calculate the derivative of a dot product is by using the product rule. The product rule does extend to dot products. Okay. All right. So with all that done, we can now go through and prove that the unit tangent and the unit normal are orthogonal. The way that you do it is you start off and say the length of the unit tangent is going to be 1. Okay. We know that to be true because that's what the unit tangent is. It's a unit vector. All right. So because of that, so after we've got that, we take t and we dot it with itself. And then by this first result that we derived, that's going to be the length of t squared. And then we know the length of t is 1 from the previous line. So we get 1 squared. So that's 1. So t dot t equals 1. And now we can go through and differentiate both sides of that result, differentiating t dot t, differentiating 1. If we do that, we end up using this second result here. It says we're going to get the product rule on this. So we're going to get t, the first times the derivative of the second plus the second times the derivative of the first. All right, they're the same, so it doesn't matter. And then the derivative of 1 is 0. If we combine these are the same. So we're going to get 2 times t dot t prime, okay, equals 0. And you can divide that 2 over and you'll get t dot t prime equals 0. And this result tells us, thus, the unit tangent and the derivative of the unit tangent are orthogonal. Okay, so what is the unit normal, right? The unit normal is equal to the derivative of the unit tangent over the length of that, right? So the unit normal points in the same direction as t prime because it's t prime divided by the length, okay? So it's a unit vector that has the same direction as t prime. So this is the same direction as n. Thus, t and n are orthogonal, since t and t prime are orthogonal. And so that goes through and proves that the two proves that the unit normal given by this equation here is orthogonal to the unit tangent. It does not go through and prove that it points into the curve. That's easy enough to prove. So let's see if we can just do that very quickly. This video is getting very long. So let's say here's our vector function. Okay. And let's pick two spots on here. Let's say here's T1. And let's go ahead and say this is the vector at T1. Let's move that a little bit. It's sitting like that. Okay. And then let's say here's the vector T2. And then that vector would point this way. Okay. All right. And then what is n? All right. So n is equal to t prime over the length of t prime. Okay. So this has same direction as t prime. And so what we want to do is just look at t prime. What direction does t prime point in? So we've already proven that the unit tangent, the unit tangent t here and n are orthogonal. Now the question is, does n point this way or does it point this way? Which way does it point? How do we tell which way it points? Okay, so to go through and figure out which way n points, it's going to point in the same direction as t prime. Okay, and over t prime over t, the length of t prime, and that's going to be in the same direction as t prime itself. So we're just going to ditch the denominator. That's basically long story short here. What I'm saying here is we're going to ditch the denominator. All right, and so what is t prime? T prime is dt dt like this, and then as we did earlier, we could say this is approximately the change in capital T over the change in lowercase t, which if you write, this is t of t2 minus t of t1 divided by t2 minus t1. And so if we have the vectors that are oriented like this, all right, so the denominator t2 minus t1, that's going to be positive because of the way that I've drawn it. So it's going this way. So we've got a positive quantity in the denominator. And so now the question is, what direction does this point in? Where does this point? If it points into the curve, then that goes through and it doesn't prove this, but it does provide an example where it worked. It gives you the general idea for why it works. All right, so how could we go through and figure out where this points? Well, they're just vectors. Let's just take the vectors and subtract them. Okay, so here's t of t1. So it looks about like that. Here's t of t2. Whoops, let's try that again. Here's t of t2. Looks about like that. And don't forget, so it points from the positive one to the negative one. Which one's positive? T2 is positive. This one's positive. The second one's positive. And so we end up with a vector that points this way, right? So it points into the curve. Okay, so that's an explanation for why the vector points into the curve. All right, so the last thing that we're going to do, and then we'll finish this up, is we'll do a quick example calculating. Let's say we want to go through and find the unit normal. So let's go through and just use our previous example because it will speed things up greatly. So we're going to stick with r of t is equal to 2 cosine t, comma t, comma 2 sine t. And so what do we need from that? Well, we need the unit tangent. Okay, and if you go through and look back, the unit tangent, right, we can just look back a few pages. We just cheat and look back a few pages. What was the unit tangent for this? It equaled this thing here. So negative 2 over root 5 sine 2 over root 5 cosine. So negative 2 over root 5 sine t 1 over root 5, 2 over root 5 cosine t. Okay. That looks good. All right. And then once we had that, we went through and generated t prime and the length of t prime. T prime was this. The length of t prime was that. We can just, well, it's probably actually faster just to go through and recalculate those, right? So t prime is going to be negative 2 over root 5 cosine t, 0, negative 2 over root 5 sine t. Oh, and then this, the length of t prime we will just transcribe, right? Right, that was 2 over root 5, right? Let's just check that one. Yep, 2 over root 5. All right, once you've got, so you can use R to find T. And again, the way that we did that is on the previous page, but you can go and look that up. Once you've got T, you can differentiate it and find its length. And then finally, once you've got T prime and the length of T prime, you can go through and divide them to calculate N, right? So we're going to get this vector divided by that number. So we're going to have negative 2 over root 5 cosine, cosine t as 0, negative 2 over root 5 sine t over 2 over root 5, right? So that's what the unit normal is. It's the t prime divided by the length of t prime. And then if you simplify that, 2 over root 5, you flip and multiply it through by this, and what happens? You get negative cosine t, comma 0, comma negative sine t. Okay. And the last thing that you can do, if you want, is you can check, did this work? Did we end up producing a vector that is orthogonal to the unit tangent? Well, you can just go through and take the dot product here, right? So here's the unit tangent. Here's our unit normal. What do we get? Negative 2 root 5 sine t times negative cosine t. We're going to get 2 over root 5 sine t cosine t. And then you're going to get 1 over root 5 times 0, so that's plus 0. And then you're going to get 2 root 5 cosine times negative sine. And so we're going to get negative 2 over root 5 sine t cosine t. And if you combine them, sure enough, we do get 0. And so the calculation here worked. It went through and it produced a vector that was orthogonal to the unit tangent, which is what the unit normal is. Okay, thank you very much for watching. Apologies for the length of this video. I hope to see you next time. Take care.